So, I just talked about solvent activity and to describe the chemical potential change from pure state to the mixtures, and this is A is the solvent, and this is your value for vapor pressure as a solvent vapor pressure compared to pure, and that's the ratio, and eventually mu A is mu A star RT. Instead of using the Rao's law, I'm just going to say that that's an activity. Okay? So this is their third representation. So point here is, this is your reference point. Okay? The reference point is pure A, right? Pure A. Pure A is your reference point. So what I'm going to do the same thing, but now this is solute. Solute activity. So solute activity is AB. And this one is following the same thing as we know. So now this one is actually, if I just write the equation, so now it's a B. This one is always true. I mean, this is, everything was described in something that is measurable values. So B is now, XB goes to 0. B is solute. This is a case. Okay? But what I cannot do is, I cannot simply convert that into the activity. This is something that I cannot do, and you should follow the logic. Just a kind of a nice logic to follow, to go through here. So this is a case, once again, now, A is everywhere. We have a little bit of the B, and B start to escape, and causing the vapor pressure of a B, and the ratio between vapor pressure B as a minor component divided by pure state vapor pressure. And this is essentially pressure difference in the pure state and the mixed state, and that's the chemical potential differences in terms of gas, Gibbs free energy at the different pressures. But now this one has a different meaning. When this is a solute, PB can be described by K, Henry's constant. How do they write? Okay. They call Henry's constant XB. Okay. You need a bigger correction factor, Henry's constant, to relate the vapor pressure with some kind of it's not pure vapor pressure, but something like Henry's constant with their mole fraction in this way. Do you remember this? This is how we do it, trying to kind of extend the idea from the Rao's law. So what I do is, I'm going to put that in, and then this one becomes KB times XB, and then becomes mu B is mu B star RT ln PB star, and then KB plus RT ln XB. Because the one at the top is just nothing but KB times XB, and I'm kind of divide it up into two portions. One containing KB time divided by XPB star. The second portion is just XB. So I kind of put it this way, with an intention to keep this one just like I did it before. I want to change that into the activity of B. and kind of just shovel that into a one new reference point. Okay, so this is a new reference point. So this equation for mu B, chemical potential of a solute, cannot be represented by chemical potential of pure state. I can do that. I'm just going to say the one that is shown up here as a mu B with standard state plus RT ln XB. Okay. So compare this. So this is a difference. Seemingly not much of a big deal. Which one is being what I call transparent? Yeah, I don't know, it's a good choice of the word. Which one is more direct and nothing ambiguous here? This one or this one?
The second.
This one. This one is nothing ambiguous. This is a pure state. This is a mixed state. This is a one, the mole fraction. That's the best case scenario. Unfortunately, it doesn't work in most of the cases. So they changed this one to A, activity A. This one always works, okay? Because now you change your description, something that is ambiguous, okay? Like used to be XA is straightforward, now it's an ambiguous. This is an A, it's just a gamma A times XA is related to mole fraction with the correction factors in between. So this is something that you can use as a fudge factor to correct. Okay? As a deviation behavior from the ideal solution. Now this is a solute. This is even more ambiguous. Okay? And my goal is to try to change that into AB. Okay? The same goal as I did before. Both are ambiguous. It's not about pure, it is pure plus Henry's constant. That Henry's constant depending on what kind of solvent you had. So it's not only depending on the B, but it's also depending on A. Okay? So this is very ambiguous. Okay? So you just pay attention to that. This is just a reference point in a way, and this is a reference being very clearly defined as a pure. So that's the difference. When you're dealing with, I want to know the behavior of this guy when they are being surrounded by something that is not. Right? If this is a case, I want to know how much of the escape and they establish the vapor pressure there. It's not going to be easy. Not going to be easy. Okay? So that's why everything is fudge factors. Okay, there are fudge factors embedded in here. There's fudge factors embedded in here to essentially to understand the activities in the vapor phase.